So hello, everyone, and welcome to this week's Autonomy Talks. This week is a great pleasure to have Samitha Samaranayake, who is an assistant professor in the School of Civil and Environmental Engineering at Cornell University. So on a personal side, when I see Samitha, it reminds me of the first ever and only, sadly, conference I could attend in person, because I met him there, and it makes me remind me of the good old times where we could travel. And it's great having me here. So something about him. He obtained his bachelor's and a master of engineering in computer science at MIT, and also a master of science in management and engineering from Stanford University. He then moved a few miles away to work on his PhD at University of California, Berkeley. And then he did his postdoc at MIT, actually working with Emilio. His research interests are in the modeling, analysis, and control of networked infrastructure systems, and he focuses on transportation systems mainly. In particular, he's interested in developing computationally efficient solution techniques and algorithms which enable practical applications. Apart from the academic positions he has held, he also worked for several companies. In particular, he worked in the server technologies group at Oracle, in the design for test at Synopsys, in the transit algorithms team at Google, and the French National Institute for Research in Computer Science. Today is going to talk about some of this work, hopefully with some outlook for the future. And we're very happy to hear what he's going to talk about. So Samitha, go ahead. The stage is yours.
Thanks, Ajay, and thank you for the opportunity. It seems like it's a group that I know, a lot of familiar faces. So it's a great pleasure. I wish it could be in person, but this is the next best. So, and hopefully we'll be back to in person soon. And please interrupt me at any point. I would like this to be as much of a dialogue as possible. I'll keep it informal. I would like to talk about, so the title is Algorithmic Foundations for Multimodal Transit Systems, but sort of the more aspirational title is how can we help better cities through better transit? And I'm going to talk about buses just because they are easier to reconfigure, but generally better cities through better transit. And this sort of aspirational title is inspired by a book from Stephen Higashide, who's a transit advocate in the US. The technical work that I'll talk about is joint work with Sid Banerjee, Shamsi Hussain, both at Cornell, and Noemi Perivier, who's at Columbia. Okay, so why are we talking about transit? There's a lot of technological innovations that's been happening in the transportation space, in ride sharing, autonomy, etc. There's a fundamental question of when can these technologies, or how can these technologies help us reach solutions that are scalable, sustainable, and equitable? And that's sort of one of the main focuses of my work. There's not that much data on ride sharing, but there was a recent report in 2019 that showed that about 40% of the travel that these vehicles are taking in the ride-hailing setting, at least, is without passengers on board. It could be just driving around waiting for a request to be assigned, or once a request is being assigned, going to that request. Now, if you look at the picture on the left, it seems like a lot of the time is actually vehicles moving around without even being assigned a passenger. And in for example, autonomous setting, that could be greatly reduced. But I'm going to conjecture that the middle part, where it's the travel going to pick up a passenger, would increase if those vehicles hadn't pre-positioned to more convenient locations for pickup. So the real numbers are somewhere in the middle. This is not meant to say what the actual multiplier is, but that there is some multiplier. And in fact, there's also some work done by Emilio and others a few years ago in the context of Singapore with autonomous vehicles. And once again, the red dots on this diagram on the right are the vehicles moving without passengers, and the blue dots were vehicles moving with passengers. And the red dots do not exist if you're driving your own car, right? So parking, of course, is something that this saves. But again, the most recent research on parking, and also with technology allowing us to get to parking spots right away, we could argue that the impact of parking is also not so much. So I'm not trying to quantify how bad things are, but rather to say that there is some impact, and that might be non-negligible. Another thing here is that these systems, in fact, the main point is that these systems doing post-negative externalities. And competition, in fact, can make these things worse. So, take a city where there is Uber and Lyft operating. And I'm going to come up with this sort of extreme example where everyone going to the airport takes an Uber and everyone coming from the airport takes a Lyft, right? And this is going to cause an imbalance between the supply and demand and cause a lot of additional miles traveled as opposed to a system where there's only one provider. Now, that's really an extreme case, but we can show that similar, even if these things were happening somewhat randomly, bad outcomes can happen in terms of the inefficiencies. Okay, and the main thing is that, again, we want people to move. So mobility is good. Mobility is good for all kinds of things: economic, productivity, social mobility, healthcare outcomes, etc. But what we want to do is control the ratio between passenger miles traveled and vehicle miles traveled. We want more passenger miles traveled per vehicle mile travel, and this is where transit can really help. So we have started doing this. There are a lot of cities that are trying to encourage high capacity ride sharing, so Uber pool type services, and first last mile transit connections. In the US, there are a large number of pilots that are happening that are trying to enable this kind of activity. And with these shuttles being run for the most part by the private sector operators, and there are also starting to be some pilots with autonomous vehicles as well. So this is sort of a good direction, and a direction that there is some traction now. And we worked with a number of transit agencies in the US. In fact, in the Seattle area, King County Metro is the transit provider. We actually have a pilot that's ongoing right now. There's some work with the Chattanooga Transit Agency as well. And we've done some work with Minneapolis, St. Paul. And of course, the algorithms for some of these work is fairly mature, including some of the work we did when I was a postdoc with Emilio at MIT. So this is there. But if you want to be a little bit more sort of bold and forward thinking, the problem I want to pose here is this question of redesigning the transit systems from scratch. So these first two, and especially the connections to mass transit, are with the assumption there's an existing transit system, right? But that transit system has not been designed in the context of using it along with these demand responsive services. So these solutions are kind of a band-aid, right? You have a system, we want to try and improve it, and we're slapping something on top of it. The question is, what if we did the network design from scratch with the understanding that these systems are now multimodal? And I'm using the example here of two systems, the transit system and the demand responsive shuttle system. But in general, it could be a whole collection of services: bike sharing, scooters, taxis, shuttles, mass transit, and all different forms of mass transit, from, I guess, in the Swiss context, from the tram to the bus to the fast trains to the regional trains. So in general, this could be a fairly complex system. But for today's discussion, I'm going to talk about it in the context of just two layers. Okay. So what is the goal? So the kind of research goal is to come up with theoretically sound and practically meaningful algorithms for these multimodal transit design problems. Okay. Any questions so far about the setup or the motivation for this line of work? And then once again, please feel free to interrupt at any point. Okay, so what is the type of system that we're envisioning here? So I'm going to call it a multimodal or hybrid transit system, where once again, there's a traditional fixed line transit service. So think of this as a bus, scheduled bus service that is now complemented by some demand responsive transit. So this could be something where you now go on your app and request a ride, and it says, okay, a shuttle will come and pick you up and take you to the bus station or the subway station, and then you will then take the subway. There will be a single ticket that you buy, and it'll take you to the destination. You could have shuttle rides on both ends, only a shuttle ride, only a transit ride, any combination of these, right? And the goal here is that you want to sort of achieve operational efficiency, obviously, but also think about sustainability and equity. And again, the claim is that the only way to be really sustainable is to move masses of people together, right? And the equity considerations are also important, and maybe we can touch on that a little bit more later on. Okay. So this is the concept. So why do we think such a concept might make sense? The one example is that in transit planning, there's this sort of ongoing kind of trade-off, that agencies have to deal with, which is the trade-off between coverage and ridership. So there's this hypothetical city where, if you can see these gray dots along the map, they are places of demand. And this is an agency, let's say, that has a budget to operate 18 buses. Now, if they wanted to maximize ridership, they would run those 18 buses on 2 main corridors that have high demand density. However, agencies are not always trying to just maximize ridership. There's a public service, so they need to think about sort of some notion of equity and coverage for the entire community. So if you take the other extreme where you're trying to maximize coverage, you would see the setup that looks like on the right. And of course, fewer people would now be transported because these buses are going to be empty most of the time because they're going on load-ins. And in fact, when I lived in Somerville, the same thing happened. I went to MIT on the bus, and there were 5 people on this big bus because there was not enough demand. But the bus still had to run because otherwise there would be no service to Somerville. So this is one of the motivations to see that whether if you have this combination of fixed and flexible transit, that you would somehow be able to get the best of both worlds. And in even some cases, increase ridership under certain conditions. Okay, so that's why we think multimodal systems might be more beneficial than traditional transit. And of course, you might then ask, why have anything be fixed and why not have everything be dynamic? Well, the trade-off there is that typically it's easier and cheaper to operate fixed line transit, and people also sometimes like to know that the bus is coming at a certain time at a certain frequency, right? So there are reasons for both, and the question is, can we get the best of both worlds? Okay, so now let's go to the sort of the research questions. Well, how do we design such a system? What are the optimization problems involved in designing such a system? I'm going to talk at a high level about 4 research questions that we are looking at, and then I'll dive deeper into one of them. The first question one can ask is, under what conditions these kinds of systems might be viable? Right? It might be not the right solution for every city and every situation. So at least 3 major factors that influence this kind of the question of whether a hybrid design system is appropriate are the cost, relative cost of operating fixed versus dynamic service per passenger. Right? If the dynamic service is cheaper than the fixed, well, in that case, there's no really incentive to having any fixed services, really, because the fixed service schedule can be, the dynamic service can then dynamically allocate that same fixed service, right? So what's typically happens is that per passenger, the dynamic service is more expensive, but the dynamism might still be worth it. Other factors are things like the OD matrix. So depending on where people want to go at what time, so the spatial temporal demand distribution might influence this, and also the network topology. Right? So we are looking at a high level how to sort of quantify this in a computationally efficient way. If a city wants to just quickly figure out under what parameterizations of their problem dynamic service is viable, or trying to partner with a company to offer such services viable. That's one high level question. The second one is, and this is the one I will talk about in more detail, is the question of which route should be fixed. So which part of the system should be operated as a fixed line service, as opposed to a demand responsive service. So this is related to the so-called line planning problem, and I will talk about this in a bit of depth. So I won't say much about it right now. The third is, well, typically when you do these kinds of network design problems, you're assuming that the demand is exogenous. But of course, the demand is a function of your system parameters and your service design, right? So we would like to be able to integrate consumer choice into such models. And not only would we like to integrate consumer choice, we would also like to integrate, what I'm calling societal goals. And this could be equity considerations. So for example, agencies are not necessarily looking to maximize ridership. They're looking at more sophisticated objectives. And we are interested in how we can explicitly state those objectives as constraints sometimes, not because sometimes they don't really make sense to put in an objective function. You could make it a soft constraint, but they do have sometimes they're legally required even to have constraints regarding certain performance criteria. Right? So the question is then, how do we integrate these into the line planning problem, which, as we'll see soon, is already a very hard problem to tackle. And then finally, the fourth piece is, well, once we design such a system, how do we efficiently operate the on-demand shuttles? Now, this, I would say, of all of these questions is the most mature area of research because it has been looked at in the context of ride sharing and ride pooling systems. However, there are some characteristics of more transit-centric services that lead to the need to think about these problems a little bit differently. So one specific example is that the reason a lot of the state-of-the-art algorithms for high-capacity, demand-responsive services work well is because very tight quality of service constraints, so time windows, for example, constrain the feasible solution space, and that allows us to use all kinds of tricks to compute these solutions fast in real time. Whereas in more transit-oriented services, the expectations are actually lower. You could have longer time windows, and this leads to computational issues. So that's just one example, but so there is a need to think about these problems a little bit differently as well. But as I said earlier, I think the three major research questions where there's a lot of work to be done are on the first three. Any questions so far? So before I sort of jump into some of the technical aspects.
Yeah, it's very interesting. Can you clarify a little bit how you model the fixed versus dynamic demand? And and what is the time scale? Are you thinking like day by day, month by month, or something like that?
Right, that's a great question. So the first thing is the demand is actually not separated as fixed and dynamic. The demand is just demand for transit, and the service provider will then decide how to serve you. So basically everything is transit, and the transit agency is operating or subcontracting the demand responsive service. So it's part of your transit pass or transit ticket. But the time, does that answer the first question? And then I'll talk about the timescales.
Okay.
Yeah, so the timescale is a great question, right? So traditionally, fixed line transit is defined over sort of some notion of daily demand because the schedule is not really changing, right? At most, there might be peak schedule and off-peak schedule. So they're looking at the average demand per some time period, and let's say it has to do with the frequency of the bus because these are capacity constraint problems. So let's say the bus is running every hour, then you might look at demand per hour, and you might run more than a bus every hour, but you're looking at demand in some kind of average sense, and then trying to design the plan that fits that demand, right? So it really depends on your operation. So if we think about this as a system that has this fixed and dynamic component, we can think about it again as looking at, let's say we are designing the peak schedule, let's say between 7 and 10 in the morning and 4 and 8 in the evening. We can look at all of that demand, like whatever the estimate for that demand is, and sort of that's exogenous to this problem. So there's some black box that tells this problem what the demand is. And then we can look at that demand as a rate. So somehow people per hour during that period, right? And then, of course, when you design the lines, the expectation is that that demand will adjust itself to when the fixed bus line is coming. The demand responsive part can adjust to whenever the demand comes, but the fixed line transit is operating at fixed schedules. So if it's running at a 15-minute frequency, you're expecting people to align their request to that 15-minute frequency or be willing to wait 7.5 minutes on average, right? And this is sort of similar to what happens in regular transit, right? So the bus is running every 20 minutes. People don't randomly show up at any point during these 20 minutes. If they know what the schedule is, they will adjust their departure times to align with the transit, right? So you can look at it two ways. One way you can look at it as look at the frequency and say the expected wait time is half of the frequency related to the frequency, or you can say people will adjust according to the fixed line schedule. Does that help answer the question?
Yeah, thanks. So basically what you're saying is that it's a little bit like induced demand in the sense that if I know the schedule, the demand will match the schedule, obviously.
Yeah, but of course, you can't have the bus run every 2 hours and expect it to adjust to the schedule, right? So it has to be reasonable.
Right.
Okay. And I think this is a really important question. So what sort of we see is that the fixed line transit will actually be very high frequency service. So it'll be a high frequency backbone because that's where it excels, right? Fixed line excels at places where there is heavy demand and therefore need to operate at high frequency. Whatever it doesn't do well is like the Somerville example, where it has to go there because otherwise people won't have a way to get from there, but it's just mostly empty. So that's the place where the demand responsive, I think, has a way to be more efficient. And maybe this we can revisit this at the end too, because the way the problem is set up might sort of also give a little bit more insight. And this is there's some modeling flexibility here too. Any other questions? Okay, so let me go. Okay, so let's talk first about the traditional bus line planning problem, right? So let's forget about the multimodal setting, because I'm assuming some of you might not have seen this. So the problem is, given a set of OD demands, find a set of bus routes and their frequencies that can serve as many trips as possible, subject to a budget constraint. Right? So basically, the agency cannot open all possible bus lines. There's a budget in terms of how many buses that they can operate. So we have let's say we have fleet of buses, some capacity C. There's a graph that defines the road topology and travel cost or travel time on each edge of each edge E. Understand the network model. We define a bus route R to be both actual route and a frequency F, right? So, bus line to be a route and a frequency. So line L1 could be route R at frequency 1. L2 could be route R at frequency 2. So they are defined as two separate lines, even though they're the same bus route. And each such line has a cost of operating the line. So the frequency could be something like 5 times an hour. Now the goal is again to choose the set of lines and the assignment of passengers to these lines that maximize ridership. And two standard assumptions to make here, or constraints of the system, would be that there's a budget B to open lines, and at most C passengers on any edge can use a given bus route, right? Because that's the capacity of the bus. Now, for the rest of this discussion, I'm going to make one less standard assumption. And this is, of course, not realistic. I'm going to assume that there are no interbus transfers. Okay. Now, the reason for this is that there's actually a hardness result. So we're going to later on talk about approximation algorithm, but there's a hardness of approximation result if you allow for interbus transfers. And again, it's something we can discuss at the end. Okay, so that's why I'm making this assumption. So it's a technical assumption. There's also sort of a practical piece here. If you're doing shuttle to bus to shuttle, people may not be so thrilled about shuttle to bus to shuttle, right? So we are saying there are no interbus transfers, but when we extend this to the multimodal setting, this does not mean you can't have shuttle to bus transfers, so there's no bus to bus transfers. Okay, so what does the optimization problem look like? So we have a variable for each passenger, a variable for assigning each passenger to a line. Okay, so the X variables here are, do I assign passenger P to line L? And VLP is the value of assigning passenger P to line L. Now, if you are trying to maximize ridership, VLP is going to be 1 if passenger P can use line L, and 0 otherwise. And when can passenger P use line L? Well, that's if the bus stops of those lines are close enough to the passenger's origin and destination, both on the origin side and the destination side. And you can also say, well, this bus doesn't take a really circuitous route to get from the passenger's origin to the destination, right? So this is a pre-computed thing that tells us whether P can use L. And if they can, it's 1. If not, it's 0. Okay, so that's the objective. So that's basically maximizing the number of riders in the system. And the constraints are, well, first question, yeah, Emilio.
Can you hear me?
Yeah.
So your objective is to maximize ridership, right? But do riders have other options, or they're kind of like stuck with the buses?
Right. In this example, there is no choice. This is the demand. The input to this is the bus demand, let's say. And like a city says, these are the people I think would want to take the bus. And I want to create a bus line that accommodates as many of these people as possible. So there's no decision making. There's no choice modeling in here, for example.
but then there is no measure of quality of actually of the ride in a sense.
There
it could
is,
be very
because
inconvenient.
no, so there is the quality that comes through V. So if there's a hard constraint on the quality, if the quality is not good enough, VLP is 0. So let's say using line L requires you walking a kilometer. Then we say that that's not feasible, and VLP assigning U to line L would be 0.
Right,
So,
but what if the route, maybe the bus stop is nearby, but then the route is very long and gets me to my destination very late.
Right. So that also would be another criteria for eliminating. So you can at a passenger, and this can be passenger specific too, right? Because this is a pre-computation step. It could be like a disabled person could have different criteria than another person, senior citizens, children, and you basically pre-compute VLP. If you know the line and you know the passenger characteristics, you just set it to 0 or 1 based on that. And that could be an arbitrary function that you define.
Okay, cool, thanks.
Only thing is it has to be sort of separable here, right, at the passenger line level. Yeah, it's a great question. Yeah, so that's baked into this. So okay, so then the question is, we have these decision variables YL, which is, do I open line L, right? Because there's a cost of opening a line. So we are maximizing under a budget constraint here. So CL is the cost of opening line L, and all the lines you open, the total cost has to be less than the budget. And the next constraint is that the bus does not exceed its capacity, right? So for passengers using an edge E on line L, that sum has to be less than the capacity times the frequency times whether that line is actually open or not, right? And the frequency is because if that line is running 2 times during this time period, so remember, let's say we were thinking about demand per hour, passengers per hour, then if it's 2, well, then the capacity is doubled in that hour, right? And this links to Andrea's question earlier about time, right? So time is only accounted for with respect to the frequency. And then finally, you can't assign a passenger to 2 lines, right? So this is the optimization problem. Any questions about the setting?
Yeah, small question is, so I guess you're imagining that each line also has a time which it travels. So
so time is implicit in the sense that this is, if you're looking at demand as, think of this as a per hour demand, it's just running during that hour. There's no specific time during that hour. So you could think about this as demand per 15 minutes, and then it would be, if the frequency is 1, that means it's running every 15 minutes. Typically for these high frequency systems, cities run every 10 minutes, 15 minutes, 20 minutes, something like that. So you basically have 3 types of frequencies that you pick from.
Okay, so basically each bus, each line
right,
is active at all times of the day at the same frequency.
Yes.
And so, it doesn't matter when people need to travel. Or not.
Exactly. And the way you deal with that is that this is a practical question again of how often can you change frequencies? You know, we can assume that in a typical city, the fixed line service can only change frequency maybe 2, like that can be the peak and off peak, right? Agencies don't like to have a lot of different kinds of frequencies throughout the day because it becomes very hard to communicate it. So typically it's just 2. So you can do a different line, solve 2 line planning problems, one for the off peak and one for the peak.
I mean, you could do it for every, so say that you want to capture, maybe there's the rush hour along, the main street of the city, like we showed.
Right.
And then the rest, like, people just going around randomly. But you cannot do this. I mean, you need to extend a little bit this, essentially. You would need to extend this to...
Well, you could solve it separately every hour, right? You could solve this problem for different demands. And if your agency is willing to change their fixed line service every hour, you could solve this per hour.
Okay.
And in fact, we envision a system. One sort of example you could think of it is, let's say Uber wants to run this service just for their on-demand system. They want to, make it more efficient and do high frequency shuttles combined with the cars. Then they could solve this every 30 minutes if they want to and reschedule the fixed lines.
Got it.
Yeah, but for transit applications, we think that's not practical. It's probably 2 is probably what they are most comfortable with. But that's a good question, yeah. Any other questions about the model? Okay, great. Okay, so turns out this sort of even this vanilla problem is a really hard problem. Well, the first issue is that there are exponentially many lines to choose from, right? Because the number of potential routes is growing exponentially in the network size. Right? So this is one challenge. Now, of course, there are ways you can try to deal with this. One is to assume, and this in fact is the most common way it's done in transit planning, is to assume that access to a candidate set of lines. Again, this set of lines can be large, just not exponential in the number of nodes. And how does one come up with this set of lines? As far as the optimization problem is concerned, it's a black box, but in practice, what's done is you could think about the existing lines in the city. You can have domain experts, practitioners, the agency input lines. You can have the public provide lines. Some companies have done that before. And you can use some data-driven methods to create lines. But as far as the optimization problem is concerned, it's a black box and it's an input. Another option, sort of if you're thinking about large-scale linear programming problems, is to think about column generation, which is a very common approach. Now, unfortunately, it turns out that, so you need to, for column generation to work well, again, you take so what is column generation? You take the LP relaxation of this and try to iteratively create the lines. This requires solving so-called sub-problem. You say that's related to the dual. It's also sort of basically the separation oracle, if you're thinking about this from an ellipsoid point of view. And turns out for this type of problem, this separation oracle is hard to compute. And in fact, it's hard to even approximate within a constant factor. So theoretically, this is not practical. There's one result in this 2007 paper that says, if you're only looking at short lines, so lines are that sort of logarithmic in the size of the network, then you can do the column generation in polynomial time. But of course, that's a big assumption. So practically speaking, you have to really assume a candidate set of lines to even solve the LP here, forgetting about the IP. Okay. Now, even if you get a candidate set of lines, the problem is still hard because it's ILP with a bad LP relaxation. And of course, again, the branch and price, which is column generation with branch and bound, is also not scaled because the column generation itself is not efficient. Okay. So the question is now, how do we tackle this problem? And our approach is, given the candidate set of lines, to show that you can provide approximation algorithm for this, and one that also accommodates a certain type of, so I have accommodates in parentheses, in quotes here, and because I'll tell you what that really means in a bit. Okay, but the goal is going to be to come up with an approximation algorithm to solve this problem, given a candidate set of lines. Okay, and once again, before talking about the actual algorithm, I'll make the link to the multimodal part here. And again, we talk about bus lines typically because bus lines can be reconfigured overnight, and sort of there's been a lot of that happening recently. And there's been a push towards more high frequency routes to improve ridership. So remember, I talked about the ridership versus coverage trade-off. Typically, the way it worked was the city would bring in a transit consultant and they would discuss and they would come up with a number pretty arbitrarily. Okay, 60% for frequency and 40% for coverage, 60% for ridership and 40% for coverage. In fact, cities are now changing that towards higher percentage of their rides being towards ridership. So Houston is the poster child for this. In 2015, they flipped the switch. Georgia, Atlanta did it a few years afterwards, and they increased their ridership routes. Okay, so once again, this is sort of something we are trying to tap into here. Okay, so the new question is find a set of bus routes and frequencies that can serve as many trips as possible. So still we are trying to maximize ridership for the model here, in conjunction with some demand responsive service that can move people around. Now we need a sort of a simple demand model here to figure out what's going on. Like I said earlier, demand is exogenous. Each passenger has an origin point and a destination point. So SPDP looks like this. If they travel by car, they would go obviously directly from S to D. If they were to take a hybrid trip, it could look like something like this. They take some line L and they finish their trip by car. They could also do the following. but that would really not make much sense because that's sort of inferior to the previous solution where they could take the bus all the way for the first leg. But like Emilio said, maybe for some reason that bus route was really long, so they had to take a car to some other point and then to take the bus. Or maybe the bus doesn't go actually from the origin, right? So these are some different configurations. And we can define a value function here. Now, remember earlier that value function that I defined was 0 or 1 based on whether it's feasible or not. Now we can define this to be something like, for example, if you're trying as a city to minimize number of vehicle miles traveled, or if you're Uber and you are trying to figure out what to do in terms of moving people purely by your taxi service versus your hybrid taxi plus high frequency shuttle service, let's say you want to minimize the total number of vehicle miles traveled. So your value of assigning a person to a certain bus line could be the number of vehicle miles saved by making that assignment. Okay, and just to make that a little bit more concrete, let's look at this passenger who has 2 options. And in the left, the bus trip is smaller, so the number of vehicle miles saved is smaller, it's 5, and on the right, you're saving 10. Okay, so this is one function that we can use to figure out the value of using the bus in a multimodal system. But again, this is again something that's pre-computed, so it does not really impact the optimization problem. Now, of course, for any passenger line combination, there are a lot of different variants in which where you can enter the bus line and exit it. And obviously makes most sense to take the one that is the maximum of these. Now, one caveat here is that this is independent of the assignment. So it might be the case that you don't actually want to take the one that maximizes the value, so that you can. Sorry, 1 second. You got it? Okay. Sorry, kids are at home today because they got excluded from daycare and one of them just ran in. Okay, so one caveat here is that when you might not want to maximize the value because if you have them take a shorter bus leg, you might actually be able to put 2 passengers on there instead of 1 at the maximum. Right? So it depends on how the capacities work of where people are taking trips. So that's a limitation of this model because we are not looking at that when assigning people to a bus. We're just assigning people to the bus that has the maximum savings. Okay, so now we can go. So in this case, you assign it to the one that has the highest value. And if you go back to the optimization problem, the only change here is now that this value function is computed in a different way. So I'm saying it's limited in the way it handles multimodality because that value function, the way it has to be pre-computed, and that has some restrictions. So you can't have you can't include a full-blown ride pooling solver to make those assignments there because that's then not sort of separable in this sense. Okay. So let's jump into actually the technical piece here, why this is hard and how one might want to try to approach solving this. So if you look at this optimization problem, it is in many ways similar to the capacity at the facility location problem. The only difference is really this capacity constraint, because in a facility location problem, you assign someone to a facility and that takes up capacity, and that's the notion of capacity. Whereas in line planning problem, if the bus has a capacity of 40 seats, you can actually have 60 people take the bus. You just can't have more than 30 people on the bus on the same edge. Right? So this is a subtle but really important distinction, because this leads to the breaking of submodularity property of this problem. And again, submodularity is this notion of diminishing returns, and this breaks that. And this is why you can't use the classical approaches for approximation algorithms for this problem. Okay, so again, the standard approaches don't work because the problem is not submodular and it has a bad inequality gap. Okay, so how do you tackle this then? So somewhat counterintuitively, the thing that works is to think about an extended formulation, where now actually we are making the LP relaxation of this problem even bigger than it is by considering all the subsets of people that can be assigned to a given line. And this extended formulation becomes a tighter LP. And because now, even though this problem is bigger, because it's tighter, it turns out that we can come up with good approximation algorithms. So let me sort of explain that a little bit more. So the formulation we use is now where we have these new variables XLS, where XLS means the set S is being assigned to line L. Okay, so we're not assigning individual passengers to lines, we are assigning sets of passengers to lines. Okay, but of course the number of sets is again now exponential in the passengers, right? Because you now think of all ways of combining passengers into these sets. And even if we have now a candidate set of lines, this problem is exponential in the number of variables it has. Okay, so that's a problem, right? However, it turns out that for this problem, there in fact is a separation oracle that can be computed in polynomial time. So we can, lazily add these sets to the problem. And that allows us to solve it in polynomial time via the ellipsoid method. So again, we wrote a bigger LP, this extended formulation, which is called a configuration LP. And it turns out that that LP is tighter. And even though there are exponentially many variables, you can actually solve this in polynomial time, because in this case, there is a separation oracle that can be solved in polynomial time. Now, once we solve the LP, of course, that's still the LP. We need to, what we care about is the ILP. Turns out that this LP formulation then actually also leads to a good approximation algorithm, and we can use randomized rounding. So the technique is similar to approach used for the separable assignment problem in this Math of OR paper from 2011. So again, the steps are write the LP, take the extended formulation, solve the extended formulation using the separation oracle, and then do randomized rounding. So, okay, yeah. So again, solve the exponentially sized formulation. It reads, so that's solving the linear program. We interpret the fractional solutions again in the LP as probability. So this is how the randomized rounding works, right? So if, so example, assignment of passenger P to line L1 is the LP gives us 0.75. So we flip a coin weighted 0.75 and assign it that if it's yes or otherwise no. Okay, now one issue here is that the budget constraint is then only going to be satisfied in expectation. Right? Now, in practice, one way to deal with this is to think of a pseudo budget. So you have your actual budget B, you don't actually give the LP the actual budget, but you reduce the actual budget by some epsilon that's chosen by the operator. And then you flip your coins. And every time you do the randomized rounding, you get an answer, which is an objective function value and a budget utilization. Now, even with this 1 minus epsilon, all you're controlling is the probability of the budget being violated, and this can be quantified. One approach that works well in practice is that you don't have to do the randomized rounding once. You can do the randomized rounding 1,000 times, and then you'll get a plot where, if you think about the x-axis, it could be the budget violation or budget used, and the y-axis could be the objective function. And of those 1,000 solutions, you can pick your best trade-off. Because again, the optimization problem will only satisfy the budget in expectation. So you can use this parameter epsilon to increase your probability of satisfying the budget, but you can also do the randomized rounding many, many, many times, in fact, thousands of times, because it's extremely fast. Because it only uses the solution to the LP, and you're only solving the LP once. Okay. And then the approximation guarantee, when you do this, is that you get a 1 minus 1 over E minus epsilon opt, again, with the budget being respected with high probability. And the epsilon here is this trade-off between the performance guarantee and the fraction of the time the budget solution is budget respecting. I went through this a little bit fast because I think I'm getting a bit short on time. Any questions about this? And of course, I sort of didn't go into the details of what the separation oracle is and how to solve this. So all those details are in the paper. I wanted to give a high-level overview. Is there a question?
I have a quick question.
Yeah.
So isn't it a problem that the optimization problem is now exponentially sized? So are you able to describe it?
Right. So good question. Let me go back to, this is a key part of this. So so now even the LP relaxation is exponentially sized, right? So that's the issue here. Now, what you can do is, even though so this is related to the column generation. In fact, that's how in practice we solve this. Even though it's exponentially sized, we know that you only need polynomially many variables to be in this. So you don't explicitly write the full optimization problem because it's impossible to write. It's exponentially sized. What you do is you iteratively add sets to the problem. And how you decide which sets to add, you use your separation oracle. So you come up with some initial sets, maybe like just the singletons, something like that. And then you can do a polynomial time check to see whether you can show either that you don't need any more sets to be added. You can prove that you don't need any more sets, or you could say, what is the set to be added? And that's what the separation oracle does. So
is this the same thing that you do for the subtour elimination in traveling salesman?
So for subtour elimination, you can lazily add cuts. Yeah. So then you have this. You again have a separation oracle for deciding whether new cuts are needed.
So it's a similar idea.
Similar technique, yeah. So the column generation, and so it's close. Like the ellipsoid column generation is sort of what's algorithmically used in practice, but the ellipsoid method is what tells us that in theory this is polynomial time. Now the column generation does not guarantee that it runs in polynomial time. It's kind of like the simplex. You use the simplex, it runs in. There's no guarantee that it runs in polynomial time, but we know LP is polynomial. The same thing with sort of column generation and this ellipsoid through the separation oracle. So both the ellipsoid method and column generation use the separation oracle, but they use it in different ways.
So the idea is that you don't write the exponential size program. You may have to ad hoc incrementally.
Yeah, you lazily add them. You start with some set, and then there's a black box that gives you a certificate as to whether this has all the constraints, all the variables you need or not. And in fact, you do it in the dual, right? So here it's exponentially many variables. What you do is you look at the dual that has exponentially many constraints, and you lazily add constraints to the dual.
Got it.
Yeah, and that's really it's a common technique in operations research, but the game is figuring out. Many problems don't have a polynomial time separation oracle. So if you can find a polynomial time solvable separation oracle or polynomial time approximable separation oracle, then you can say something. If not, it becomes hard. And in this case, it worked out well, but in the candidate line generation problem, the separation oracle is not nice. You cannot solve. You can't even approximate that. So in that case, we needed some external black box with no theoretical guarantees to tell us the candidate set of transit lines to consider. Whereas in this portion of picking the sets of passenger assignments, we can do it exactly. Any other questions?
I have a question.
Yeah.
Well, thanks, Professor, for a great talk. If this is the end, maybe there's a little bit more. But I was thinking about the assumption that you don't have any line transfers. And I know you said there's some formal results on that.
Right.
But I was trying to figure out where that comes from. And I was thinking about, encoding the transfer as another line. Combining the two lines, but I think the problem with that, if I'm correct, is this constraint on how many people can ride each line. So is that where that approach falls apart?
Exactly, that's the right intuition. So you can show that you can show a hardness of approximation result that there is not even a constant factor approximation when the case of when you have multiple lines. So sorry, not line to line transfers. And it is because then you have to consider if you're only considering combinations and certain combinations, that's fine. But if you're allowing people to both go on the line by itself and a combination, you have no way to attribute the capacity because then it's coupled across these two assignments, and that breaks things.
makes sense. Thank you.
Yeah. And so the two hardness results are that you need to have a candidate set of lines that you cannot do exactly, and you cannot do these line-to-line transfers in the design itself. But of course, in practice, once again, we can argue practically that if you're doing shuttle to bus to shuttle, then you might be okay to not consider bus to bus transfers. But if you're doing, bus only planning, that's absolutely necessary. But you cannot, at least in this kind of framework, you cannot solve that exactly because there is this hardness result. So happy to take more questions, but as I'm also going to quickly show some results. This is first a synthetic network with a time budget of 20 minutes to compute solutions, varying the set of passengers as candidate line said. So we try a lot of different configurations just to get some sort of sensitivity analysis. So one is considering the original IFP, so give it to Groby versus try our approximation algorithm. Right? Now, of course, when the candidate set of lines is small and the problem is small, the ILP, solving the exact ILP does better than our algorithm because I mean, it's exact. If the problem is not too big, it can solve it exactly. But as the problem gets larger and larger, the ILP just cannot comes up with bad solutions or just completely chokes because it takes too much time to solve. You can similarly, this is for a fixed passenger set. You can also increase the fix the set of candidate lines and change the passenger count, and again, same thing happens. Right? And we also ran it on something which is maybe a more sort of real world data network. Again, this is from, in fact, it's not New York City taxi data, it's New York City limousine data, which has slightly longer trips than the transit trips, because for transit, it makes no sense to take a data set that has so many very short trips. Again, we can see that the ILP, as the budget increases, quickly struggles, whereas our algorithm does better. And I also have to say that our algorithm is sort of coded somewhat naively in Python, and we are comparing against Gurobi that is fully optimized. But even in that case, as the problems get larger, the approximation algorithm does way better. For full disclosure, I have to also say this, but of course, if the budget is so high that you can pretty much open all the lines, then of course, again, the ILP runs very fast and does better. So the problems are only hard in this middle, where there are many feasible solutions that are very close to the optimal solution, and the ILP really struggles, whereas our approach is pretty robust to this. Right? Yeah, so then of course, this is sort of the punchline is we want to bring all of these things together to make these things operational. So I talked about one part of this, but there are many, many factors to this. And I think there is a huge opportunity here, but very little research relative to all the other exciting areas of transportation in the transit-related questions. That hopefully some of you start looking into transit-related problems. I would say one last thing, because this is very much an autonomy-oriented group, that I think sort of one of the biggest practical issues for these kind of multimodal trips, at least in the systems in the US, is the labor issues. So if you're a transit agency and you want to hire a shuttle driver, you have to pay them the same amount you pay a bus driver. These are unionized jobs. So the economics of operating shuttles is not so great because it costs almost as much as a bus. So what agencies do is they subcontract with Uber type companies, TNCs, transportation network companies, because then the labor laws related to contracting with them is different to contracting with shuttle systems. But all of these things disappear, I guess, if the systems are autonomous, because then the smaller shuttles will be relatively cheaper than the bigger buses. I think there's a huge amount of opportunity for sort of autonomous systems to help make transit better. So yeah, thank you. And I'll sort of leave with some related questions. These things I already talked about a little bit. How do we incorporate the endogenous nature of demand, do pricing, mechanism design related questions when designing multimodal systems, etc. And finally, the full paper of what I talked about is on archive. It's also published, and I'd like to thank the funding agencies and partners. And thank you very much for your attention.
Thank you, Samitha. Very nice. Very nice. Nice talk and very nice work. If I may ask a question, or actually, I would like to make a point. So, actually, what we have found, the people talk a lot about ride sharing, right? So, to reduce VMT and things like that. What we have found is that actually ride sharing. So the only situations where ride sharing works are the situations in which you'll be better off by having a line service on that route. So I think that, the kind of thing that you're doing is actually very, very useful. As essentially you want to get those routes where you would see that you have enough of a volume of demand that you will fill shuttles if shuttles were offered, right?
Right.
Then you may just as well have buses, right? Or, and then run it as not as an on-demand shuttle or bus, but as a line service.
Right.
And the thing that, this is really the right combination. So what you need to do is an on-demand service with small vehicles plus a line service with larger vehicles.
Right.
With size and frequency, that you need to work out what are the best economics, right? And the quality of service and the cost and things like that, right? But I think that the combination of the two really resolves a number of these issues of how to offer something that is sustainable, but also something that people will actually use.
Yeah, that's a great point, because in the paper, the way we wrote it actually in the Sigmetrics paper is in that way, as not for a transit agency, but for a company who is now trying to mix some kind of backbone shuttle service with fully demand responsive service. And is, for example, every hour re-optimizing their fixed lines, because the passengers don't even see that in that case, right? It's just it's just, you go on the app and you get a ride, and the system, it connects you to a bus, but it's not a published bus. It's just an internal way of splitting the trip. I think this is part of your question is also what we were trying to think about in this, first question of under which conditions should we use hybrid transit systems? Because, to your point, again, the dynamic components don't always work well in many settings. Most of the trips that are shareable maybe should be fixed. But again, this depends on people's willingness to incur detours, people's willingness to have waiting times. If people have very strict quality of service constraints, then the shuttle combination might not work well. It depends on the demand distribution. It depends on so many components that it's hard for us to say what's good. And we would like to have some formal way of actually quantifying that. And we are trying to think about this from a multi-stage stochastic optimization point of view, because when does dynamism help? The question we are trying to formulate something called the value of dynamism and see when is the value of dynamism greater than 1, in which situations. And that again, dynamism helps when things are time varying and when things are uncertain. So, because the fixed lines, if they have to be the same set of fixed lines, and this again depends on the service type, because the transit agency, they have to be fixed for most part of the day. They can't change frequently. In that case, even time varying demand requires dynamic service, right? Also, uncertain demand requires dynamic service. So there's a question of under which input parameter configurations are dynamic services useful. And I don't think we have much idea of, you mentioned some things that you've seen, but we don't have mechanisms for sort of formalizing this and understanding this as far as I can tell. So I think that's another important problem, basically what you just said.
Yeah, very good. Yeah, thank you, Samitha. Very interesting.
Any other?
I have a couple of questions. I can start with one and then see if others want to speak.
Sure.
Let me choose which one. Okay, maybe that's an easy one. So the talk basically addressed the first vertical bar here, right? You're ensuring operational efficiency, right? Now, how harder does including sustainability and equity, I'm thinking maybe more about equity, makes the problem? Because sustainability, I can guess, it's just a matter of miles driven, and then you have some factor. At least that's usually how it is addressed in mobility.
Right.
But what about equity? So,
right. Great question. Yeah. So the sustainability kind of, like you said, comes for free if you use transit, because you're now putting, again, the metric would be vehicle miles to passenger miles, that ratio. But the equity question is more involved, right? So one of the things we've been looking at is, again, in this sort of third row here of how do we integrate consumer choice and societal needs. If you solve the line planning problem, you can then solve a pricing problem to achieve a certain, so let's say you want to do some welfare maximization. In the objective function, instead of the value function that we currently had, we could have a welfare maximization value function. And when you are trying to, and then you can, you can then a posteriori compute prices that allow you to obtain that solution under certain settings. Now, and in this framework, it turns out that we can also write constraints that are respect to groups of people. So you can say there are, let's say that a simple setting, there's a group of low income, economically underprivileged community and everyone else. And maybe you want to say each group should have the same level of service. So the percentage of people served from each group has to be the same. So anytime you can write linear constraints in the original network design problem, it turns out that you can actually solve the pricing problem to achieve that distribution. So the way, at least we are looking at trying to incorporate equity is through such constraints in the design problem. And then in the theory, you can show that as long as those constraints are linear and for reasonable sort of some classes of choice models, the MNL being the easiest because it's invertible, but also more discrete distributions as well. So that paper should be on archive very soon, by next week, I think. So that's the approach. Now, of course, the problem with equity is that everyone has their definition of equity, and like people in optimization trying to talk about equity isn't not always consistent with the social scientist notions of equity. So this is really important question that is, I think, far from resolved. So we are trying to also talk to people who work on equity. In fact, Cornell, we are trying really hard to hire people. There's an opening for a position for someone who does optimization and equity, and we've searched really hard to even see who we should reach out to in the infrastructure space, and that intersection is almost zero of people who have really worked on equity and who understand how to do this sort of in a methodological way, like from optimization point of view. So just we have some ideas, but that's far from the perfect answer to your question.
Okay, great. Well, that sounds interesting. Maybe since it's connected, I'll quickly go with the second one, which is, so a lot of this goes through how you define these V's, right? These rewards or costs for people. How much can you describe things like congestion dependent values or time dependent values, or I'm thinking about congestion pricing and these kind of things. How can you incorporate these things into the evaluation of the reward?
It's a great question. So since this is a planning problem, it's not operational. As long as you know these things ahead of time, you can incorporate it into the line cost and things like that. So into the line cost and the value function, right?
That's clear.
So maybe the simple answer is, as long as it's something you know in advance, and it is, and automatically, if it's something that's fixed in advance, it has to be independent of these decisions, and then it becomes trivial in some sense, right? Because it's all pre-computation. Then it's not a The problem is if it were to be coupled, and I think those problems are harder in the operational problems as opposed to the planning problems. So for the real-time shuttle routing problem, those things will be complicated. But for the design problem, if you assume it's sort of exogenous to this, and it has to be if it's pre-planned, I guess, then it's easy.
Okay. Yeah, that's good, because you could theoretically include all the congestion models you want or whatever. You simply pre-compute and solve.
Right, exactly. And it does not alter the hardness of this problem, because those are all pre-computation steps as far as this optimization problem is concerned.
Cool. Okay, I'll leave the stage to the next questions. If you have questions, simply unmute yourself. Or I can go with another one.
Yeah.
Maybe, I mean, it's not exactly the problem we want to solve, but I was kind of thinking about it when you were showing that you tried the different budgets to compare the algorithms. You could think of a case in which actually the budget is not given, right? And you want to find out the budget. What is your budget? Well, it depends how many people pay for which service that I'm offering, right? And so you have kind of a fixed point there. Have you looked into that, like profitability of? I know we always think about this in terms of you provide a service as a city, but if I offer a shuttle versus I offer a bus, I can change the prices and so on. That gives me the budget.
Yeah, that's a great question, right? So, I think from the transit perspective, usually there's a transit budget, and it's exogenous. But if you were a shuttle, if you were like a Uber or whatever company, then it would be different. Now, the budget itself, in this case, since demand is exogenous in this model, the budget, I guess the way you would have to do it as the budget would have to be a function of basically the objective.
Exactly.
So, it would still be linear, but I would need to check whether, I'm inclined to say that won't mess up things, because that is not the complicated constraint here, it's the capacity constraint. But I would need to check that the separation oracle still works. It should work, because it's just that constraint is not, it's still a linear term there. But I would need to check to give you a exact answer.
I'm asking because this could drive decisions such as taxation of other private mobility options. That's something we're looking into, right? So maybe you want
sorry, say that last part again.
So knowing this exact behavior could influence decisions such as how the city can put taxations or incentives on other private mobility providers, right? Based on how much you can do that on your own, you seek money or help from others that are using the resources.
That's a good question. I mean, we've looked at this in a different model that doesn't fit our approximation framework here, but within this framework, I think you could still do. Another thing you could do is also you can do binary search on the budget. If there's a certain sort of thing you want to look at, you can run it for different budgets and do that. I mean, that's not sort of from an algorithmic perspective, that's not really interesting. But yeah, in practice, if you want to try out a few things, you could do that. But I think you can explicitly incorporate that into the budget, as you're saying. I see why that could be useful, and that's a great idea. Yeah.
Thank you very much. Right. Any final question? Okay, I think it's good. Thank you very much, Samitha. Great talk, great point of discussion. Wish you good luck for the next steps.
Yeah, thank you. Thanks again for the opportunity and all the discussion. And good to see everyone. And
I will follow up with some with the link for the video and so on.
Sure, that's good.
Thank you very much.
Bye. Good to see you, Emilio. Bye.
Bye-bye.
Bye-bye.